Hello everyone. In this video, I'm going to cover the lessons for week 5. If you open up the course schedule, you'll see that week 5 is the first week of our algorithm analysis unit. In this week, we're going to talk about algorithm analysis in terms of big O notation and growth rate functions. We're going to analyze recursive algorithms and many sorting algorithms. In L5-3, we'll cover sorting algorithms that you may have already covered in a previous course. And then next week, we'll cover merge sort and quicksort, which more than likely you didn't cover in a previous course. But if you have, then that is great as well. So let's get started with L5-1. So learner objectives for this lesson: understand time and space complexity, discuss why it is important to analyze algorithms for efficiency, and introduce and talk about big O notation. So in the beginning of your computer science education, it was enough to simply solve a problem. We wanted you to solve it with good style and good practice, working on modular designs and good variable names and commenting your code. But in terms of the actual efficiency of the algorithm you were implementing, we didn't care so much. We wanted you to get practice writing code and solving problems. But now, at this point in your computer science education, it's not enough to simply solve a problem. We want to solve a problem in the most efficient way we can. That way, as our problems start to get bigger and bigger, or our data sets start to get bigger and bigger, our algorithms are going to take hopefully a reasonable amount of time. If we implement them using a brute force solution and we need to apply this brute force solution to hundreds and thousands or even millions of items in a list or an ND array or an n-dimensional ND array or a pandas data frame, then this might take a long time if we are implementing our algorithm in an inefficient way. So today we're going to talk about how do we measure the efficiency of an algorithm, and the answer is in terms of its complexity. And we look at complexity in two main aspects: the time complexity, meaning how long does it take it to run. Also in terms of space complexity, meaning how much space does it take the algorithm to run, meaning how much memory is needed for the algorithm to run. We're going to focus on time complexity in this class. We will touch on space complexity on a few topics, especially when we talk about hash tables and hash functions, because we'll often have a trade-off between time and space complexity. So let's talk about time complexity. Time complexity lets us compare two solutions to the same problem and decide which solution to use because it is faster, meaning it has better time complexity. To determine an algorithm's complexity, we count the number of times each operation in an algorithm occurs. This count is called the growth rate function, often abbreviated to GRF, and represented using a notation such as T of n, where n is the size of the problem. Now, you are familiar with this notion of n being the size of a problem. For example, when we talk about the number of items in a list, we usually let n represent this number. So the size of a list will directly dictate the efficiency, or directly be related to the efficiency of an algorithm that needs to operate on, say, each item in that list, all n items. So let's take a look at an example to help us understand what a growth rate function is and how we can derive one. So I have a very simple example here. It's a function that prints a list. It's called printlist. It accepts a single argument, a list that is not nested, stored in terms of a parameter called a list. So using a while loop, we walk through each element in a list and print it out. So I want to keep track of every single operation that occurs in this Python code. So first, the first line in the body of printlist, I is assigned 0, we have one assignment. And then for our loop, we have n plus 1 comparisons, I less than the length of the list. So there's n comparisons for each iteration of the loop, and there's that one extra one in the end when this Boolean condition evaluates to false, and we break out of the loop. Now, inside of the body, we have a call to print, and this will occur n times because this loop body is going to execute n times. We also have our progress towards our Boolean condition being false, I plus equal 1, So we have n addition assignment combos here. So if I sum up all of these operations, I have a growth rate function, t of n is 1 plus n plus 1 plus n, which is 3n plus 2. So our growth rate function, t sub n, for the function print list, the algorithm for printing every item in a list, is 3n plus 2. Now, some of these operations are negligible. So in terms of the efficiency of needing to walk through each item in a list, I don't care about these plus 2 operations here. Those are negligible. And in fact, even this 3 is negligible too. It's a scaling factor for really the bulk of the work being done, which is walking through a list of n items. So this is kind of the idea behind big O notation, is we're going to grab the most dominant term of a growth rate function and use that to represent the efficiency of an algorithm in terms of time. So the dominant term of a growth rate function t of n is called the order of the algorithm, and it is represented in big O notation by a big letter O, which is short for order. So big O notation is used to denote time complexity, and for this problem, the dominant term in t of n is n. It's linear. So as n gets large, the constant 2 is insignificant in terms of the efficiency of the algorithm, and the 3 is a negligible scaling factor. So let's take a look at some common time complexities to give you a sense of the different classes of algorithms that we typically write. So starting with the fastest, big O of 1 is called constant time complexity. And what this means is an algorithm that has efficiency big O of 1, constant time complexity, takes the same amount of time to run no matter what the size of the problem is. A good example of this is inserting at the front of a linked list. No matter how long a linked list is, if we always insert at the beginning of the list, we only need the head pointer, essentially, to insert a new item. This is constant time complexity because the size of the problem, meaning the number of items in that linked list, does not matter to insert at the front. We're simply going to update the links. No traversal is required. Next, we have logarithmic. So logarithmic represents repeated division, repeated making a problem smaller and smaller by a factor. For example, binary search. If you have a sorted list and you need to find an item in that list, you can repeatedly have the size of the list to search for in binary search. This is a logarithmic function because we repeatedly have the size of the problem, and the log base 2 here represents that half. Next is linear time complexity, big O of n. We saw this example in our print list function for example number 1. And this is also an example with linear search. Anytime we have to walk through n items in order to find something, or perhaps n items in order to print something out, then that is going to be linear time complexity. Next is log linear. So this would be n log n. A good example of log linear functions or sorting routines such as merge sort and quicksort, which we will cover here soon. Next is quadratic and squared. This would be an example of a list operating on a list with a nested loop where each loop traverses n items. An example would be quadratic sorts such as bubble, selection, and insertion sort. Cubic, n cubed, example would be matrix multiplication. So perhaps you have a triple nested loop, and each one of those loops is going to iterate in terms of some size of the problem, n. And we can see that we could go n fourth, n to the fifth, so on and so forth. Those are called polynomial algorithms, and they are, in fact, somewhat fast. When we get down here to talk about our slowest class of algorithms, they are very slow, and polynomial algorithms are much more favorable or desirable over an exponential algorithm, for example. So our slowest algorithms are exponential algorithms like 2 to the n, 3 to the n, any power raised to the n, even n to the n, very, very slow. N factorial. Some examples of these types of problems include Towers of Hanoi, recursive Fibonacci. These are all examples of our slowest algorithms. I really like this plot here because it shows the relative speed between these different types or classes of algorithms. So logarithmic down here is very fast. If we can ever get a log function, a log growth rate function, or a log big O for our big O, that is great. We would love to have that in as many cases as we can. Constant time complexity, I mean, even more great, but many problems cannot be solved using constant time complexity, such as sorting. You cannot have constant time complexity for a sorting routine. And then linear, log linear, and then we start to see kind of rapid growth here with quadratic and cubic, but neither of these can even compare to exponential. If you look down here, our x-axis is n, the size of the problem. It becomes quickly too difficult to implement on a computer in terms of how long it's going to take to run. So let's take a look at another example here. Suppose we have a two-dimensional list and we want to sum all of the items in the two-dimensional list. So here's a function sum2dList that accepts a nested list argument stored in the parameter a list, and it walks through each item in the list, which would be like a row, and then it walks through each item in a row, which would be each item in the nested list, and it sums up each item and then returns the sum. So let's take a look at the growth rate function for this example. So we have two assignments in the beginning, the first two lines of the body of our function. Sum is assigned 0 and I is assigned 0. And now we get to our loops. So we have n+1 comparisons for our outer loops Boolean condition. And then we have n assignments. So n times this body is going to run. So we'll have n j is assigned 0 assignments. We will also have n I plus equal 1 assignments. This is our progress towards our Boolean condition being false. Now we have this inner loop, and this inner loop is going to run n times, and the body of this inner loop is going to run n times as well, assuming this is an n by n two-dimensional list. So we have n times n+1 comparisons. So there's n+1 comparisons that will occur here, and this loop is in a loop that will run n times. So we have n times n+1. And we have our summation here, which will occur n times in part of a loop that runs n times. And we have our progress towards our inner loop Boolean condition being false, j plus equal 1, which runs n times n times. So what we have here is 2 plus n+1 plus n plus n plus n times n+1 plus n squared, which is 2n squared. Oh, this is 3n squared, excuse me. So we have an n squared here, n squared is 3n squared. We have n, 2n, 3n, 4n, and 2 plus 1 is 3. So we have 3n squared plus 4n plus 3. So our big O of this growth rate function here is n squared. So this is a quadratic time complexity algorithm. So here's another example for a linear search. So we already know that linear search actually has time complexity big O of n, linear, because I used it up here as an example. But you can see where this big O of n is coming from, because here's a list that walks through each item in the list. And so in general, n comparisons will have to be done if the target is either the last item in the list or it isn't found. So we always think about our big O notation in terms of the worst case scenario. The best case scenario for this would be perhaps the target is the first item in the list. In this case, linear search has big O of 1, constant time complexity. but that is usually not going to be the case. So we always try to overcompensate by talking about an algorithm in terms of its worst case time complexity. So let's take a look at these cases in more detail. So the best case performance for an algorithm describes the algorithm's behavior under optimal conditions. For linear search, the best case scenario is if the item to find is the first item in the list, yielding best case performance of big O of 1. So this best case performance represents a lower bound on the performance of the algorithm. The special notation omega is used to represent the best case performance. So for linear search, this would be omega of 1. The worst case performance describes the algorithm behavior under the worst possible conditions. For linear search, the worst case scenario is if the item to find is the last item in the list or not in the list. So we would have big O of n. Worst case performance represents an upper bound on the performance of an algorithm. So we have omega, our lower bound, and we have big O, our upper bound. So when the big O time complexity for an algorithm is equivalent to the omega time complexity for the algorithm, then we would say that theta is the tight bound of the algorithm, meaning the algorithm's lower bound and upper bound are the same. And then average case performance for an algorithm describes the algorithm's behavior under average input conditions. We won't go into detail about how to find the average case for an algorithm in this class because input is so varied, it's so diverse, it is really difficult to mathematically formalize the average case based on all types of input. But for linear search, we can say with confidence that the average case scenario is still a big O of n because each item is equally likely to be the target. So the algorithm will check n over 2 times on average, and n over 2 is still the order or the dominant term is still n. So I have some practice problems here that I will not go through because I have listed the answer for each one of them. I encourage you to work through these on your own for extra practice. Now let's move over to the next lesson, L5-2, where we're going to look at recursion. So you learned recursion in 121 and 131. Recursion is a method of solving problems by breaking down a problem into increasingly smaller subproblems until the subproblem is small enough to be solved trivially. This is our base case. A recursive algorithm is an algorithm that solves a problem using recursion, and they typically have the following characteristics: a base case, progress towards the base case, and some kind of recursive calling itself. So when we think about recursive solutions, we typically think about recursive functions. That would be a function that either directly or indirectly calls itself. So a classic recursive algorithm that is covered in 121, 131, and many Intro to CS courses is binary search. I have listed here iterative solution to binary search and a recursive solution to binary search. I encourage you to review the code for both of them and be familiar with how the algorithms are implemented. What I want to say about recursive binary search is we have repeated division by 2. When we compute our mid, which determines how we can frame our searches for a target in a sorted list, repeatedly dividing our problem in half. We're making it half as big each time. So this repeated division by 2 is represented by the mathematical function log base 2 of n. So because of our mid get start plus end integer divided by 2, we're always going to have the amount of search space we have to look for a target. So this is a logarithmic function. Average case and worst case are logarithmic, and the best case is omega of 1 with early exit. That would mean there would be some code that when the target matches the current value at mid, then the function is going to early exit and not search any further. Another recursive example that I would like to go over is this toy example here. I have a function called f1. It is recursive. It accepts a single parameter n, which is an integer number. The base case for this recursive function is when n equals 0, we stop recursing. When n is greater than 0, then we recurse 3 times. So for every call to f1, while n is greater than 0, we have 3 more recursive calls. So essentially, in terms of the problem of n, we're having repeated multiplications by 3. Now, I made this diagram here to show you what the call tree would look like for this function. So let's say we call this function f1 initially with a value of n set to 3. And 3 may not seem that big, but even building the call tree for 3 took quite some time because there are a lot of nodes here. So we come in f1 of 3. Okay, this is our first call. And we test, is n greater than 0, 3 greater than 0? Yes, it is. Now we call f1, passing in n minus 1, 3 minus 1 is 2, and we have f1 of 2. Now we come in f1, n is now 2, is n greater than 0, 2 greater than 0? Yes. We call f1 again, passing in n minus 1, 2 minus 1 is 1, and now we have f1. Now n is 1, n greater than 1, yes. We come in, now n is 1, now we call f1 again, 1 minus 1 is 0, so now we come in again, and f1, n is 0, n is not greater than 0, there's nothing else to do in this function, so now we return back to the previous call on the call stack, which is the first call to f1 of 1. So now we call f1 again with 0 again. We stop recursing, we come back. We call f1 again with 0, we stop recursing, we come back. Now we are finished executing the body of n greater than 0 when n is 1. So we pop off the call stack and we're back up to the call where n is 2. And we just finished the first call for n minus 1, 2 minus 1 is 1. So now we repeat this again. That gives us this subtree in the call stack. When this finishes, we repeat it again a third time. When this finishes, we come up, and now we've finished the first call when n is 2, and we come back up to our initial call, and we repeat again for n minus 1, 3 minus 1 is 2, and now we repeat this subtree again. When this finishes, just like this call, we repeat again for this subtree over here, and when this finishes, only then does our initial call to f1 with n equal 3 return. So the time complexity for this algorithm is actually exponential. So we have repeated multiplication by 3. Every time we call f1 and n is greater than 0, we call f1 3 more times. So I have here that each level of this tree is the number of calls is a power of 3. So 3 to the 0 is 1 call, 3 to the 1 is 3 calls, 3 to the 2 is 9 calls, 3 to the 3 is 27 calls, and you can see how if we had 3 to the 4, 3 to the 5, etc., how we would have number of calls equal to 3 ways to the power, and the power represents the level in the call tree. So worst case, average case, 3 to the n, and the best case would be n is 0 and we don't actually recurse at all, and then this would be omega of 1. So I have some more practice problems here that I encourage you to work through. I have the answer listed for number 2, so you can check your work. Now let's move on to our last lesson for week 5, analysis of sorting. I'm going to go through this lesson somewhat fast because many of these sorting routines are review from your previous classes. And I'm also going to make a video where I run through a few examples of these sorting routines if I have time. So review of sorting routines. In this class, we're going to cover selection sort, bubble sort, insertion sort, shell sort, merge sort, quick sort, and heap sort. So in this lesson, we're going to cover these 4 sorts, and then we'll cover merge sort and quick sort in the next week. And we'll cover heap sort several weeks from now when we learn about priority queues and their implementation with heaps. So for each algorithm, when we're thinking about the time complexity, we can solve this by computing a growth rate function, counting the number of comparisons and the number of data swaps, and then take the largest order term there to get our big O time complexity. For one of the programming assignments you're going to complete in this class, you will go through and count all of the comparisons and data swaps to estimate the total work done by sorting routine algorithms. So selection sort is one of the easiest sorts. It's typically the one that is taught to beginners because it is the most common way that we think about sorting something. So the big picture algorithm behind selection sort is select the smallest item in the unsorted portion of the sequence and add it to the sorted portion of the sequence. This will, each iteration, increase the size of the sorted portion and decrease the size of the unsorted portion. Here is an example running selection sort with some random data, size 20 for ND array, and printing it out before and after it's been sorted. The time complexity for selection sort, average case, worst case, and best case is quadratic and squared. Here's a great practice problem for you to work on to make sure that you're familiar with selection sort. Use it to sort a linked list. Bubble sort is also a common algorithm taught in introductory computer science courses. The big picture behind bubble sort is to perform pairwise comparisons, swapping data such that the largest items in the unsorted portion of the sequence bubble to the end and form the sorted portion of the sequence. So it's called bubble sort because the largest items bubble to the end. So your sorted portion grows from the right end, the largest end, down until there's only one item left, and a sequence of one item is itself sorted. Here's some code here that runs on a 20 item ND array, again, random data, and sorts using bubble sort. Average case, worst case, n squared, and then best case is omega of n with early exit. So practice problem number 2 has you go through and figure out how to implement early exit for bubble sort. So we want to improve the algorithm so that sorting stops once the array is sorted. Now we have to walk through the list one time to find out if it's sorted or not. So that's where our n comes from here. Insertion sort, this is probably a new algorithm. The big picture behind insertion sort is to build the sorted portion of a sequence by inserting items into their sorted position in the sorted portion of the sequence. And I have an example here that I recommend walking through. Initially, insertion sort starts with one item in the sorted portion. So one item in a list is sorted by definition or by default. And then it goes to the next item in the list and finds out where to insert that item into the sorted portion of the list. So here, 3 needs to go in the position of 4, and that means 4 and everything to the right of it, which in this case is nothing, but it soon will be something, needs to be shifted down. So insertion sort inserts in the sorted position and shifts down to make room to insert this new item in the sorted portion of the list. Implementation of insertion sort. Time complexity, average and worst case, big O of n squared, and best case with early exit, omega of n. Now, shell sort is an interesting algorithm. The big picture of shell sort is to perform repeated insertion sorts by sorting every item in a gapped sequence until the gap is 1. Now, a gapped sequence comprises items at position 0, 1 times gap, 2 times gap, etc. And then shifted over by 1 would be 1 plus 1 times gap plus 1 times 2 times gap, etc. So the best way to really work with shell sort is to work through examples because this idea of a gap is hard to grasp until you see it perhaps on paper or an example walk through step by step. So In my algorithm I implemented here, I initialized gap to n over 2, so powers of 2 will be my gaps. But this may not often be the best case for a gap. How to choose gaps is a highly researched area, and I have a link here if you want to read more about how to choose gaps. But for our introductory implementation for shell sort, using powers of 2 for our gaps is going to be just fine. So here's an example here, but I also walk through sequence to sort for shell sort, one pass at a time. So I'm not going to go through this example verbally in the video because I wrote it so that it's standalone and you can follow through at your own pace. But it goes through each one of the gap values. What are the indices, meaning what are the items associated with those gap values, and how insertion sort is used to sort each gap. And eventually the gap will become 1, which would mean that what's left to sort is the entire list in sorted order. Here is an implementation of insertion sort. And if you would like, I also included this list I used in the initial example up here that you can uncomment and run shell sort over and implement print statements at key spots here, and then you can walk through and see how is shell sort sorting this list in terms of my example. Now, shell sort is our first sorting algorithm that's not quadratic. It's actually n log n, average case, worst case, and best case because of this repeated division by 2 for our gap. So shell sort is a quite efficient sorting algorithm. And I have some practice problems here that I encourage you to work through for extra practice. With that, this concludes our week 5 lesson notes. Let's take a look at the course schedule to see how learning these sorting routines fits into next week's lessons, where we're going to learn about merge sort and quick sort. So we just finished L5-3 covering selection sort, insertion sort, bubble sort, and shell sort, and then we'll learn about merge sort and quick sort. And later in the course, on L11-2 or somewhere in week 11, we'll learn about heap sort, and those will be our 7 algorithms covered for sorting routines in Computer Science 215.